The first speaker is Matt Baughman. He is a PhD student in the University of Chicago, and he's been looking at this topic of tournament-based pre-training that I think can have large implications for how we do federated learning in many specific types of contexts. So I'm going to stop sharing, hand over to Matt, and then we can see what you all think and ask him a few questions. Over to you, Matt.
Cool. Thank you, Nick. Let me quickly share my screen. Hopefully it's still working from when we tested 2 minutes ago. You see it all right?
Yeah, it looks great.
Cool. So yeah, like Nick said, I'm going to talk to you a little bit about this method that I think saying that we developed it is a little bit of a stretch, but we kind of repurposed this for use in federated learning, and especially federated learning in austere environments. I'll talk a little bit about the collaboration that kind of gave rise to all the different needs that went into us deploying this, and kind of the current tests that we're doing, what our interests in federated learning are. Because I have a secret to tell you. I am not a machine learning person. I'm not a federated learning person. I am by trade a systems person. So I'm part of this group called Globus Labs. Some of you may have heard of Globus. It's a company, startup, nonprofit, kind of whatever you want to call it, that was spun out of the University of Chicago back in the late 90s, I believe, 98 or 99. That focuses on very, very, very large scale data management. So we're doing large management across different institutions, companies on the scale of petabytes per client. And we're closely integrated with Argonne National Laboratory, so working with the large scale systems there. This group was kind of born out of this collaboration called the Computation Institute, which has now been adjourned, I guess you could say. But the whole idea was we wanted to operationalize these computational resources for real science. A lot of academia in general, but especially computer science applications focus purely on kind of, can we do this? Do we get good experimental results? But one thing that we love about Flower, and it's a vision that we share, is really operationalizing these methods for real scientists, real people out in the field. So that said, my main focus is on kind of cost-aware computing and creating these dynamic systems that allow folks, specifically domain scientists, to use large-scale supercomputers, as well as including devices that range from these supercomputers all the way down to very, very small edge devices. My belief is that people should spend time on their own science and not have to spend time on doing the system stuff. That's what I'm here for. So we have several kind of ongoing missions with regard to this. One of our big projects was previously called FuncX, now called Globus Compute. It's a serverless framework that effectively allows folks to push compute and push data wherever they want. We call it a fluid execution framework. It's also designed to be extremely lightweight, but also extremely scalable. So we have great scaling tests going all the way down to kind of these single core smart devices that are running off of tiny battery packs and solar panels living out in the forest somewhere, all the way up to scaling to thousands. I think maybe we've even reached tens of thousands of nodes on the largest supercomputers, top 10 system kind of class. This has since, you'll see the architecture diagram shows that it's still called FuncX. This is because it's a little bit older. It has since been rolled into a semi-commercial product with Globus called Globus Compute. But it's the client side is still open source, so anybody here who wants to go try it out is more than welcome to go try it and use it for their own research and purposes. But the kind of vision that we see stemming out of this type of technology is a national, what we call a continuum, a computing continuum of facilities and compute resources for science. So there's this great system in the US called ESNet, the Energy Sciences Network, that connects, I believe it's 29 science user facilities across the United States with high priority, high bandwidth interconnects. And these include many supercomputers, including currently the top 2 systems in the world, soon to be the top 4. hopefully, as well as many actual experimental science user facilities. So in this graphic here, we have the major accelerator laboratories across the United States, because the data collected from these, I think, totals somewhere close to a petabyte a second. Obviously, you can't store that, but you have to process it in time, and then distribute the relevant information across the entire ecosystem. Obviously, if you started a streaming transfer of anywhere close to a petabyte a second, even a terabyte a second between these different locations, people would probably get upset. And so we're thinking about how we can create systems to automate what's important, pre-process what we can, and move what we absolutely have to. Because of this kind of multi-site component, and especially the aspect of having to distill this data before we transfer it, a lot of folks are really interested in federated learning, because they can effectively distill the data or compress the data by training a model on it at their local sites, and then just move those, quote unquote, just move those models around. Still very large models in many cases. But this also enables faster sharing of information. Some of the labs have semi-strict controls on what can and cannot be transferred or made publicly available. But this is effectively a manner of privacy preservation for some folks, data management for others, and really operationalizing that data that's, say, collected at the Argonne accelerator. We can send Berkeley a model that they might be able to use to drive experiments at their synchrotron facility. So kind of the collaboration that's currently going, I talked a little bit about the Computation Institute and how I got here as a systems person. But now we do have this project called Rural AI, which is a large collaboration. I think we're up to 7 or 8 institutions now. It might even be 9. Of folks that are really interested in bringing these AI tasks to small and large devices alike, but enabling AI in areas that historically don't really have AI-enabled technologies. We chose the name Rural AI because a lot of our applications are very agricultural, especially in developing countries or in areas of countries that don't have substantial access to heavy compute infrastructure. We've done a lot of work with native peoples in several different countries, looking at how we can potentially accelerate agricultural investment, agricultural knowledge by providing these types of services, and kind of decrease this idea of the digital divide between the compute haves and the compute have-nots. Many of these restrictions, poor network, stranded compute, very stranded data, are obviously problems that people are continuously solving. How can we do the most with what we have? But we really found that federated learning is a massive way that we can leverage the data and the compute that is available to not really waste, because that's the big thing here is we're trying to prevent computational waste, which is for all of us spending time on ChatGPT, which guilty. But we're burning cycles. As a systems person, that's a mandatory hobby. You have to be willing to burn cycles. But we want to make sure that for people in areas where these computational cycles, energy, network are valuable and precious resources, that we can use these resources as well as possible. This little robot here we have at the bottom is a great example. It goes through and it can measure all types of characteristics about soil quality and takes pictures of plants and weeds and pests and things like that. The problem is it produces about 3 gigabytes per second of data, which even with a semi-fast wired connection is a tenuous amount of data to continuously stream. And so this is kind of our main use case, is how can we process that data, selectively choose what data we want to learn on, and use the onboard resources in order to train small models that we can then hopefully use to regenerate data and produce even larger models in concert with dozens of others of these devices. Because this data is very noisy and it's very large and we can't offload it, we wanted to find a use case that could somewhat simulate the conditions that we see. So one of these data sets is the Wellington camera trap data set from New Zealand. It is a very unique data set because there are lots of well-labeled images, and it's wonderful, except the subjects of each of the images are relatively obscure. This is one of the more obvious images. You might be able to see the bird, which now I put a bounding box around. This is definitely in the top 10% of visibility. And so it's highly non-IID data, highly sparsely featured data. And you also have the problem that it's a massive noise to signal ratio because the images are roughly the same each time, except for perhaps a bug or a bird that's flying past the camera. Birds love this, animals love this because they have natural camouflage. But it makes it difficult for us to do interesting things with it, especially with the very constrained resources present on these devices. You can't run even the largest of the kind of state-of-the-art object detection localization networks like a YOLO won't even have a fighting chance on smaller resources like these. So we have to find kind of low barrier to entry ways in order to handle this. Additionally, remember, not a machine learning person. And so we want to find ways that are accessible to domain scientists that not only they can understand, but that are plug and play and don't require gross amounts of configuration or domain knowledge. And so the problem that we're kind of running into that we're trying to solve with these simple methods is the fact that with this high noise signal ratio, a lot of these features get washed away over time. We actually find, which is hysterical, and there are definitely ways around this. The individual models do relatively well, but they are definitively overfit. We've tried the standard repertoire. I should say our machine learning people, the proper machine learning people, have tried ways of ensuring that these models don't overfit. Then we end up really not learning too much about the individual animals, especially since some of the classes that we have double-digit examples, where others, like birds, we have over 100,000 images of birds. So not to mention that we have, again, these compute constraints. And in order to kind of prevent this washing away of learned features, so you kind of have to learn features to a level that they will survive this averaging, this aggregation across all of the different endpoints, but at the same time not overfitting. So we thought that, if there's some way to align these features prior to doing aggregation, prior to doing kind of more what we would consider proper federated learning, training and aggregation, this might give, in the process of gradient descent, kind of a point, a good starting point, something that will say, hey, we have these features that we think are possible. Now, how can we double down on them? And so if we can align these features prior to training in a given training round, we thought this is a pretty good bet of being able to at least prevent some of this washing away when we're aggregating over hundreds of endpoints. There are definitively methods that are much more technologically savvy, also much more compute intensive, that involve a lot of math to compute similarity vectors across different features, order features by order individual kernels by the features that they've learned, do aggregation in kind of a piecewise fashion. But like I said, not only does this take more computational resources, it requires generally a level of understanding that many domain scientists might not have, and we don't want to assume that, especially since federated learning in its core is a relatively simple process, but the learning curve becomes very steep very quickly. We want to make sure that kind of 0 to 1 is simple for scientists, where they might be able to say, hey, would my data set work? and not immediately get bad results and say, oh, federated learning, it's terrible. We never want to use it again. And so we came across this paper at SC a couple of years ago called Livermore Tournament Fast Batch, where basically they were training individual models on their individual systems at Lawrence Livermore Lab and taking the most performant network, most accurate network at each round, and then just distributing that as a global model versus doing some fancy aggregation. I'll just put this whole thing up. And so we thought, well, what if we do this and then distribute whatever that quote unquote best performing model is as the global model. And this way we kind of start with a semi pre-trained network that has that provides a grounding point of these aligned features for all models to start with, rather than just doing kind of standard random initialization. Again, there are much smarter, much more involved processes to do this. Definitely not claiming that this is state of the art by any means. This is the kind of 0 to 1 point for aligning features. And so by doing this process, we can begin to learn features and distribute those features globally versus doing this aggregation that will wash away the less strong features, especially for categories like the individual animals that we have maybe 10 images of. So the results, in some cases, they're very, very good. In some cases, they are not so good. What we really see here is that for a smaller number of endpoints, this does allow us to get over that issue of averaging away features. The problem is once we start doing this with too many endpoints, a lot of the distribution, the non-IID-ness, really just relies on kind of the luck of the draw. And so we don't get universally good results much above kind of the 60 to 80 endpoint range, just because no single endpoint has enough data to actually make a meaningful impact. And in some ways, it can ground the entire training process such that you might not be able to recover because you kind of get stuck in these local minima, and you can't really recover without injecting some sort of noise, randomness, etc. We do see additionally, if I run back to this graph, a lot of these training rounds just sort of ended on the same value. It was very uninspiring. The funny thing is we tried a very wide hyperparameter sweep. Again, systems people, so we like the brute force approach. And we always arrived at kind of the same answer. So we believe it's just a characteristic of the data because the largest class composes about 12%. And so it's really just learning the largest class and parroting that every time. But in this case, we see substantially more variability round over round, even beyond the pre-training round. And we think that's because grounding on solid features, then each model can kind of deviate from the pre-trained features as its data might require. But eventually the vast majority are going to kind of average back to this set of pre-aligned features. One thing that we're thinking about with this is potentially we could interleave tournament-based pre-training with traditional FL and take that approach. That might have good results, but we aren't sure at this point. Right now we're working on validating this across wider data sets, greater set of architectures and different resource and endpoint configurations. So conclusions, future work, like I said, we really just want to generalize this. We want to see in quote unquote more real science use cases if this is beneficial, or maybe we just found the one application where it does so poorly that any type of perturbation to learning features might kick us into a beneficial training regime, but it doesn't apply anywhere else. So we are currently running tests. We're actually hoping to have them for this meeting so we could show off, haha, this applies to all these different training scenarios, but Unfortunately, because the supercomputing conference deadline is coming up, all of the machines are largely reserved for people who aren't just running spin loops. Or I should say, are reserved for the people just running spin loops. So where does Flower fit in? This specific work, because we're just effectively playing around, did not use Flower initially, but we are currently working to integrate this with Flower, because like we said, Flower's vision really parallels our own, especially the use of real devices and also being able to do simulation, we think is huge. And so we want to integrate this method along with our other kind of FL-related workflows with Flower, both in simulation on the large machines, but also our real-world test bed. We're working on scaling Flower just to see kind of, how far can we push it before it breaks? So far, the answer has been we can push it really far, which is awesome. And we're thinking to definitely pie in the sky idea, and I'm sure that the Flower people will tell us that we're crazy and we shouldn't do this. But we're looking at the potential of integrating our Globus Compute serverless framework as the sort of communication backend for Flower. So using all of the Flower strategy specifications, input-output specs, but using this kind of serverless backhaul to be able to access these more remote devices that you definitely have to use sort of a fire and forget model, and kind of managing the communication ourselves. We have some students working on this, and we'll hopefully see good results, but like I said, we're not entirely sure. So at this point, I'll take questions. My email's at the bottom if you want to ask any additional questions offline, and then I also have a QR code to my Google Scholar there in case you're interested in my systems work versus my pretending to be a machine learning federated learning person. Thank you, guys.
Thank you. Thanks for the talk. Very interesting concepts. Anyone, if they want to ask questions, you could raise your hand. I could unmute you. We've got the Slack and other types of inputs. So anyone want to kick things off with a question?
Yeah, first of all, thanks for the great talk. And I just want to comment about the last thing and say not crazy at all. I think this is a very viable path forward to integrating Flow with other kinds of infrastructure that is already in place. And I think Flower Summit at Flower AI Summit next week will have some very good news for you, because what you're planning to do will become quite a bit easier.
Awesome. No, I'm definitely looking forward. Unfortunately, I can't come in person, but we'll definitely attend virtually.
We're also very pro systems people, so no need to have a big divide here. We're a big tent. Love system people, love machine learning people. I think I saw Javier had a question. Let me just allow him to talk. I'll click this button. Javier, I think you can speak.
Yeah, can you hear me?
Yes.
Yes. Okay. Yeah, I think this was super interesting talk. I have one question, a bit more machine learning, but I think it's very high level. So I think one of the problems when doing federated learning is, especially in the wild, like the example you were showing with these cameras in New Zealand, is that you don't have labels. So was your training doing some kind of unsupervised training, or do you think that's the way to go for this kind of super large scale federated learning systems?
Yeah, so in this case of this data, so I'll give you kind of two answers. In this data set, one of the reasons we used it is because it's almost 300,000 images, and they did have each one was hand labeled, which is incredible. Big citizen science effort. So that was kind of the main reason behind using that. Regarding unsupervised learning, though, this is a huge push, especially with the applications that we've started looking at, and the folks that we've started talking to in kind of these domain science areas, especially experiment steering, having kind of a semi-supervised learning approach, where we can see like it's very easy to tell if an experiment ended poorly or successfully And then we can kind of backtrack and do almost a reinforcement learning thing with federated learning, potentially, across multiple sites, just to, like I said, with the synchrotron experiments, doing this kind of experiment steering where every part of the experiment relies on accurately and predictably rotating these samples so you can get the proper imagery from the synchrotron radiation. It's definitely not a solved problem. People have ways of doing it. But these are cases where you can't kind of go through and say, was this a good rotation? Was it a bad rotation? So there are definitely applications for unsupervised learning, especially like you said too, in these austere environments where we have to delete 99% of the images and can only transfer one out of every I think it's about 200 to 300 images. So being able to do accurate unsupervised learning, automated clustering is definitely something we're looking into and something that's going to be very important.
Yeah, I think it's super cool. Thanks.
Thanks.
Yeah, very cool. I think there is a baseline in Flower for doing single image unsupervised learning. So basically SSL combined with FL, if you want to check it out sometime. Or we can point you to that. Let's see, there's a question here. The question is, are endpoints analogous to clients in FL?
Yes and no. So our endpoints in Globus Compute is really you can think of it as the client very generally, where that is the kind of point of contact with the central for us manager, forwarder, for you guys, aggregator, server. However, in the Globus Compute case, each endpoint can have many, many workers, which you can think of as many, many clients potentially, each running its own machine learning task, especially in the large systems. These individual workers generally end up being single nodes, and your workflow is going to have some sort of inherent idea of parallelism that it can abstract on its own. But we also definitely recognize people who use individual workers on individual cores to do parallelism in that way. So yeah, long answer to your short question, you can have clients on the node level, the endpoint level, or the system level, really. Like if you were using a 10,000 node machine, you wouldn't want 10,000 endpoints. You'd want one endpoint and then some way to plug into the scheduler to control the rest of the resources.
I see. Okay. Yeah, that was an anonymous question from the audience. I think we're a little bit low on question time. Yeah, I think we'll end it there. But that was a great talk. Had some good questions there, and fascinating work. I like the fact that you've acknowledged that, federated as a method for training models is much more than just focusing on privacy, but it is an answer to many of these kind of underlying system issues where you might have you have a compute plane, you have a data plane, and you want to get a model trained in the best way possible. And this recipe is really powerful for certain situations. So cool, very good.
Yeah, thank you guys so much for having me. Really appreciate it.
Yeah, thank you.